So molecular shape and polarity. We've talked about what a polar bond is, where we have unequal sharing of electrons. So if you have a diatomic molecule with just two atoms, if the bond is polar, then the molecule is polar, right? Because one end will be more negative than the other. So here in a hydrogen chloride molecule, the chloride side is more negative, and the hydrogen side is more positive. And so we say it has a dipole, and it's a polar molecule. When you have a polyatomic molecule, more than two atoms, then you have to look at the geometry. Because depending on the geometry, the dipole moments from polar bonds can cancel each other out or not. So let's look at carbon dioxide. Carbon dioxide has two polar bonds. And let's refresh our memory on how do we decide if it's polar, a polar bond. Look at the two atoms. If they are not the same element, assume it's polar. The only exception I want you to remember is carbon and hydrogen. A carbon-hydrogen bond is nonpolar. Otherwise, if the elements are different, assume that it's polar. So here we've got two different elements. Not up there, down here. Carbon and oxygen, different, so we're going to assume it's a polar bond. Oxygen is more electronegative. It is, we can predict that by its position on the periodic table is closer to fluorine. So oxygen's more electronegative. It's going to hog the electrons from carbon. And so this bond has a negative end at oxygen and a positive end at carbon. This bond on the other side is also polar, and the negative end is with oxygen and the positive end is with carbon. So the arrows help. I'm going to draw them up here so that we can actually point at them. So we can represent those polar bonds as arrows pointing towards the more electronegative element. If you imagine that these oxygens are playing tug-of-war and the carbon is in the center of the rope, these oxygen atoms are the same. They're equal strength, equal electronegativity. So as they're pulling on the rope in opposite directions, is the rope going to move? No. They're at a draw, right? They're both pulling, but there's no net movement of the rope. So this is not a polar molecule, even though it has polar bonds, because those dipoles cancel each other out, just like people pulling in opposite directions cancel out the effort. So we would say that these vectors add up to zero. And we'll talk about vectors. Vectors are quantities that have a direction and a magnitude. So the direction of the vector points from the less electronegative to the more electronegative element. The magnitude is proportional to the electronegativity difference between those two atoms. If it's a large difference, the magnitude is larger. If it's a small difference, the magnitude is smaller. When you have identical atoms here, then the magnitudes are identical and they're in opposite directions, so they're going to cancel each other out. So this molecule, even though it has an uneven electron distribution, we can't say that one end of it is more positive than the other. Any questions about that? Let's look at water. You just look at the formula, water and carbon dioxide look, well, CO2 and H2O, two of one of the other. But when we look at the molecular shape of water, we learned on Monday that water is a bent molecule because of the two lone pairs on the oxygen. So the molecular geometry is bent. Well, we have dipoles here. Oxygen's more electronegative, pulling electron density away from hydrogen in this direction and from hydrogen in this direction. But this would be like someone playing tug-of-war. So you've got, this is Dad, and he's playing tug-of-war with his two little kids, right? And they're pulling at an angle to him, but he's stronger. So is Dad going to be able to pull these kids across the room?
Yeah.
Yeah. They're pulling at angles from him, but he's pulling away and he's stronger. It's not that he's in the middle and they're on opposite sides. Then nothing would move. It's at an angle, and so the whole thing will move. So these vectors do not add up to 0. The magnitudes of these dipoles are the same, but the angle means that they don't add up to 0. So what we have is we've got this vector and this vector, and vector addition says that we'll have something like this. The sum of those would be in this direction. So there is a net vector. Water is a polar molecule. The oxygen end is slightly negative. The hydrogen end is slightly positive. And that has a tremendous effect on the properties of water. Any questions? Oops. So I'm going to tell you the more rigorous scientific way of determining molecular polarity, and then I'm going to give you a shortcut way that works most of the time. So the rigorous method is first you need to draw the Lewis structure, determine the molecular geometry of the molecule. Then look at the bonds. Are the bonds polar? If all the bonds are nonpolar, like in a compound containing only carbon and hydrogen, you can't possibly have a polar molecule. You have to have polar bonds for a molecule to be polar. So determine if the molecule has polar bonds, and then identify those with vectors pointing towards the more electronegative atom, with the length being proportional to the difference in electronegativity. Then decide if those polar bonds add together to form a net dipole moment. If they do, if there's a net vector, the molecule's polar. If the vectors add to 0, the molecule's nonpolar. Sounds simple, right? No, it doesn't sound very simple. It's kind of complicated. So I'm going to go through this quickly because it's not that necessary. Vector addition, a couple of examples. So here we have vectors in the same direction in a line, right? So here we have two vectors. Their magnitudes are the same, both positive 5. They're both pointing to the right. So this is a lot like adding numbers on a number line. So here we have to the right 5 and to the right 5. So that adds up to the right 10. Here we have two vectors going in opposite directions, but their magnitudes are different. So we've got 5 in the negative direction and 10 in the positive direction. That adds up to a net positive 5. Here we have opposite directions equal magnitude. Pointing in opposite directions, so negative 5 and positive 5, and those add up to 0. So this would be a case where you can have polar bonds, but no polar molecule, right? Like the carbon dioxide. What if they're not just in a line like that? What if you've got 2 dimensions, or heaven forbid, 3 dimensions? Draw a parallelogram, put the two vectors on adjacent sides, and then finish the parallelogram. So you've got the two vectors, and then you finish a parallelogram. And then the sum of these is from the corner here where the vectors meet to the opposite corner. So those two vectors, let me just do an example. So let's say we had a vector that went like this and one that went like that. So what we'd want to do is we'd want to draw a line parallel to this one. So, oops, not very good on here. And then a line parallel to this one. And then the sum of those two vectors is from this corner to the opposite corner of the parallelogram. So that's the sum, vector addition. This reminds me of a meme I saw on Facebook. For those of you on YouTube, it is April 11th and tax day is coming up. And I saw this meme the same day I was helping my son with his taxes, and it says, "I'm so glad that I learned about parallelograms instead of taxes, instead of how to do my taxes. It has come in so handy in this parallelogram season." Right? Well, there's the parallelogram, so at least there's some use for parallelograms. 3 or more vectors, what you do is you pick 2, add those first, take that sum, add it to the third. Okay? This table shows us common cases of adding dipoles based on molecular geometries. So if you have a linear molecule, it's generally going to be nonpolar unless the magnitudes of those dipoles are different. If you have a bent molecule with polar bonds, it's probably going to be polar. Trigonal planar, if the vectors here, if the differences in electronegativities are the same, then this one's going to be nonpolar because they're going in opposite directions. Tetrahedral could be nonpolar if you've got them, all the magnitudes are equal. If you've got a magnitude that's different, then it won't be 0. Trigonal pyramid is typically polar because of, because of the shape. Okay, so that's all good. That's the more rigorous method. Here's a shortcut method that'll work most of the time. And I think that's pretty good, working most of the time. So a molecule is nonpolar if both of these conditions are true. There are no lone pairs on the central atom, and all the atoms bonded to that central atom are either the same or they have the same electronegativity. So no lone pairs on the central atom, and all the atoms bonded to it have the same electronegativity. The molecule is going to be nonpolar. So I'll do a couple of examples. So let's look at ammonia. We do need to understand the Lewis structure. So we can't get away from that because we need to know if there's lone pairs on the central atom. So we draw the Lewis structure for ammonia. And we do end up with lone pairs on the nitrogen. So the shortcut method looks at this, says, are there lone pairs on the central atom? Yes. We don't need to go any further. This is polar. And I'll show you why it's polar. What shape is that molecule going to have? 4 electron groups with 1 lone pair. It's a tetrahedron with 1 side missing. It's a trigonal pyramid. Right? So trigonal pyramid, we got this one coming out towards us and this one going back. And we've got vectors. The nitrogen is more electronegative. So these are polar bonds. And if you understood the vector addition thing at all, I think you could see that those are not going to add up to 0. You could also think of, well, if this person's playing tug-of-war with these guys and they're, spread out at an angle like that, is the whole group going to move? Yeah, they are. So it's a polar molecule. Any questions? Predicting polarity is very important. Some of you are going to be going on to take organic chemistry. Polarity of molecules is very important in OChem. So let's determine if CF4 is polar. What do we have to draw first? Lewis structure. So put the carbon in the middle, and the fluorines around it. Count up the electrons. Distribute them. There's our Lewis structure. Does this have polar bonds? Are carbon and fluorine different? Yeah. Yeah. I thought I said chlorine there for a minute. Carbon and fluorine. Those are different elements. It's polar bonds. Is the molecule polar? No. So, shortcut rules. Are there any lone pairs on the central atom? No. Okay, condition 1 is met. Are all the atoms bonded to the central atom the same? Yes. So both conditions are met. The train agrees with me. So this is nonpolar. Then let's look at why that is. What is the molecular shape of this molecule? Tetrahedron. So, which is more electronegative, fluorine or carbon? Fluorine. So, these polar bonds are vectors pointing towards the fluorines. Can be a little hard to visualize. But that carbon has 4 vectors pulling on it. They are equally spaced in 3-dimensional space, and they are equal in strength. And so if you think of somebody in the middle and people pulling on them, there's not going to be any movement. Nobody's going to win. These vectors add up to 0. Any questions? It's really mostly about the lone pairs. What if we change one of these? What if instead of fluorine here, we've got iodine? Are there lone pairs on the central atom? No. Are all the atoms bonded to the central atom the same, or do they have the same electronegativity? No. Condition 1 is met. Condition 2 is not met. This is a polar molecule. So in our picture down here, if this is the iodine, is iodine more or less electronegative than fluorine? It's less electronegative. The difference in electronegativity between carbon and iodine is going to be smaller than between carbon and fluorine, and so this is going to be a little stunted vector. Are these vectors going to add to 0? No. They're equally spaced, so they're opposing each other, but one of these is weaker, and so these guys are going to overcome it, and there will be some movement of tug-of-war players. How do you play tug-of-war in 3-dimensional space? I don't know. But in chemistry land, you can do anything. Your question? It would alter the angles here slightly. That's not very significant in terms of the bond polarity, but yes, it would. The iodine is larger than the fluorine, and so that would cause these fluorines to be squished together a little bit. Yeah. But the big thing is that the dipole moments are not the same magnitude, and so it wouldn't add up to 0. Any questions? Okay, so why do we talk about this? The polarity of a molecule has a big effect on the properties of the molecule. So oil is a nonpolar molecule. Oils are primarily carbon and hydrogens, so nonpolar bonds, and so they are nonpolar molecules. Water is polar. It has a bent structure and polar bonds, so it is a polar molecule. Oil and water do not mix, do they? Think of Italian salad dressing. There's the oil and there's the vinegar. The vinegar is an aqueous solution of acetic acid. So you've got the water and the oil, and you can shake it up and pour it on your salad, but then you set the bottle down and it separates again, doesn't it? Do you ever wonder why? Why does it do that? It has to do with the polarity of the molecules. So here are two water molecules, and we can think of them as being somewhat like magnets. These are electrical charges, but electrical charges often behave like magnetic charges. We are more familiar with magnets because we've played with them as children. We use them on refrigerators to hold up notices, etc. So this dipole in the molecule can be attracted to the dipole in the next molecule. The positive end of this water molecule is attracted to the negative end of that water molecule. And so they will tend to stick together like magnets do. Oil, being nonpolar, does not have the same sort of attraction. So that would be like non-magnetic things. So here we have the solid marbles are magnetic marbles, and the glass marbles here are not magnetic. And so you can imagine what would happen if you dump a bunch of these magnets together. The magnetic marbles are going to stick to each other, and they're going to push the glass marbles, the non-magnetic ones, out because there's no force of attraction between them. And that's exactly what oil and water do. The water molecules are attracted to each other, they bunch up, they stick together, and they push out the oil molecules. The reason that the oil floats is because it's less dense than water. But it's polarity that causes it to separate into two layers. Any questions? So if you have maybe been baking a cake and you had to grease the pan and get Crisco on your fingers and cover it all over, or if you've got butter on your fingers because you were eating something yummy, can you just rinse that oil or butter off with water? No, because oil and water don't mix. How do you get grease or oil off your hand? You got to use soap. So what's so magic about soap? Ever wonder how soap works? Let's tell you how soap works. So here's an illustration of a soap molecule. Most of the soap molecule is this long carbon-hydrogen chain, which is nonpolar. But at one end, there's a polar head. There's some oxygen atoms. And so this end is polar. That's attracted to the water. This nonpolar part is attracted to the grease or the oil. So what happens is, red's not a good number. So here's our grease, chunk of grease, right? And then use black for the soap. So the nonpolar tails of the soap are going to be attracted to the grease or the oil, and they'll get in there and mingle with those molecules. The polar head part of the soap molecule, well, that's not very good. Let's fix that a little bit. Is going to be on the outside because it's not going to mix with the grease very well. So all those tails are going to be stuck inside this little globule of grease, and the polar heads are on the outside. And then we've got water out here, and water's polar, and water is attracted to those polar heads. And so the water sees this, and it's like, oh, you're one of us. It's hiding this nonpolar grease inside of it, but on the outside, you just have these polar heads. And so the water's like, yeah, you can pass, come on through. Whereas the oil, it would say, no, wait a minute, you can't come between us because we don't like you. You're different. So what soap does is it breaks the grease up into small particles and allows them to suspend in the water and be rinsed away. So that's what soap does. Any questions?